Okay, to increase the temperature of a mole of gas by delta T, then, we've seen that the total translational kinetic energy has to increase by 3/2 R delta T. And for diatomic gas, you have two rotational modes, each requiring the same kinetic energy as each translational mode. Now, we have three translational modes, translation in the X, Y, and Z directions. And we have two rotational modes. They all get the same energy. Now, if the translational kinetic energy increases by 3/2 R delta T, by how much does each mode of translational energy increase by? The answer should be fairly clear. It's going to be 1/3 of this, or 1/2 of R delta T. So each mode of kinetic energy carries 1/2 R delta T, or changes energy by 1/2 R delta T when the temperature changes by delta T. Okay, so if we have three translational and two rotational modes, 1/2 R delta T change in energy for each of them, then the translational mode requires, okay, again, I'm just repeating what I just said. Each of your translational modes requires this: how much energy to increase the temperature of 1 mole of diatomic gas by delta T? The answer clearly is, again, 1/2 R delta T for each mode, each translational and each rotational mode. It's got to be 5 times 1/2 R delta T, which is 5/2 R delta T. So for a monatomic gas, the change in U, and I'm using U for the internal energy, the kinetic energy, total kinetic energy of the gas molecules, is 3/2 R delta T multiplied by N, the number of moles, because 3/2 R delta T is what you get for 1 mole. If you multiply that by the number of moles, you get the change in the internal energy. And for diatomic, it's the change in internal energy, change in the total kinetic energy of all the particles, is 5/2 R delta T multiplied by N.